while ago, actually a long time ago, I promised to make a video on these two topics. So today we will answer the questions. How does the formula lmsdfjdsfjlsdjhfsdslkfjnkfdslndgnf work? And what exactly is a limit?
Take that! It's a function. That's very simple and also very cute. Now we want to find its value at x equals 0. Oh no, it seems like the function is now undefined at 0. What do you mean? Can't we just factorize and cancel out the x? Well, you see, my little walnut, every other time we cancel the x, we unknowingly assume that the top and bottom are not 0. But now they are 0. And we get 0 over 0, which is illegal. So this ominous white point here just indicates that it doesn't exist. But wait, we ran into the same problem in the last video. And what did we do? We took values very near to the point. So for this example, we can also try smaller values for x, like 0.1, 0.01, you can see that the function gets closer and closer to 3. But that's not all. You see, you'll have to approach the point from the other side as well. And now we can confirm that the limit of this function as x approaches 0 is 3. Recalling the notation from the last video, we can write it like this. But still, why need two sides? Because sometimes this sort of function exists. Well, in this case, the limit from the left is now 2. Therefore, the limit for this scenario does not exist. So to sum up this part, we have a function that should be easy to factorize, but this condition screwed it over. So when we see an obstacle, we, try to get around it. And it turns out by finding values really close to it, not only can we factorize the function, but we can also use it to find an accurate limit.
Well, this isn't the only way to find the limit. In fact, there's one more that I'll cover later, but for now, I realized that I haven't talked about this name yet. Put simply, the first principle of anything just means that it's the basics of something. And in this context, every derivative rule or law that you see stems from this one formula, hence the name. Moving on.
Let's start with a simple example. Y equals x squared. We want to find its derivative. Quick recap, substituting delta x equals 0 right now yields 0 over 0. So let's first try expanding. Remember, delta x equals 0 doesn't let us factorize as well. But remember how we tackled this previously? The values around it allow us to. Now we can safely let delta x go to 0, well, closer to 0, and end up with this. Let's move to another example. Seems like factorization isn't a usable method now. So we now move on to the other method of finding limits. Remember how to remove surds from the bottom of a fraction? Well, we're gonna do exactly that, but the reverse. Let's multiply both sides by this expression, which you may remember is called the conjugate surd. This really is just factorization 2.0. I mean, come on!
And that's it! That's all the textbook really has. Ow! But guess what? There's way more things to do with limits. I mean, come on, it's calculus, but given how little motivation I have left, I've decided to only cover one more thing. Sadly, I roughly covered one of these things in a previous video, the one on circular measures, so go watch that, will you?
Up until now, we kept saying that the limit is just some value that a function gets really close to. So get this. I have this function and I want to find its limit as it goes to infinity. You'd obviously say 0 because, yeah, just touch the axis, goddammit.
But what if I use this line of logic, since the value technically also gets closer and closer to -1? So why can't I say that the limit is -1? It's clear that we need a more rigorous definition for the limit.
Even though the limit does get closer to -1, there is always some distance that the value can't actually cross. Say we can't find the value of 1 over x that has a distance of 0.5 from a line here. But if I set the bound to be 0, I can find a point like that. It's right here. Even better, we can also find a shorter distance than that. Here, and here. And heck, give me an even smaller number, as small as you want. Do this as much as you please, I can still find the value within that distance from 0. Henceforth, not only can we put this question to rest, I will also present to you the formal definition of the limit. Given the function f of x, let its limit to a be called L. For every epsilon more than 0, there exists a delta more than 0, such that for all real x, if x has a distance of delta from a, then fx has a distance of epsilon from L. If you're still watching this, honestly, thank you. And you may also be wondering where I've been all this while. So basically, I filmed this in around December and edited this in around May and June. And in between all these months, I barely had any time to film or even touch the editor. As it turns out, college can really take up a lot of your time. Nonetheless, to all of my loyal subscribers out there, I am really sorry for keeping you guys waiting all this while, but I'm glad that this video is finally out. Also, I've posted about this before already, but the next video will not be a continuation to the derivative series, but an entirely new topic. Given how I'm still in college, I don't actually know when that next video will be released. But stay tuned. In the meantime, don't forget to like and share this video, and also subscribe to this channel, because I really wish to keep this channel going. And that's it from me for now. Bye!